much, Darby. Got it. Thank you very much. It's really been a pleasure to be part of this team and to be interacting with so many of you. I mean, in fact, I can't see all of you, but I know there's many of you there that I've collaborated with in the past. So it's been very enjoyable. So I'm going to tell you about work that we're doing as part of COINFLIPS to generate random numbers with magnetic tunnel junctions with a specific way of doing it that I'll explain. But first, I want to mention that this is really a large collaboration. It involves principally people at NYU who are doing measurements or analysis, Laura Ream, and a collaboration with a particle physicist, Andy Haas, an undergraduate, Andrei Durovsky, and an engineer, Michael Soy, and then collaborators throughout with Sandia, Spin Memory, even KTH, University of Virginia, UIUC, and Jonathan Sun, who I've been collaborating with for many, many years on spintronic-related research. So you'll see their names pop up when I show the publications, but we've had a lot of very close interactions that have made this work possible. So I'm going to start by telling you about magnetic tunnel junctions. I'm going to assume that I'm talking to a pretty broad audience that don't think about magnetic layers too often. And then I'll talk about the specific materials and devices that we're working on, which we call stochastic magnetically activated random transducers. And they're a type of way of generating random numbers with nanoscale magnetic tunnel junctions. I'll talk about how we make random bit streams with this at could be close to gigahertz rates in principle. And now it's megahertz rates. And I'll show you the effect of the environment. Basically, we're using magnetic tunnel junctions to convert entropy in the environment into a random bit. So the environment is very important, and understanding its role is important in devices. I'll talk about operating conditions and also some work we've done modeling device-to-device variations. And I'll show you what we're really excited about right now is getting to faster data rates and larger data sets. So toward the end, and then I'll summarize. If there's questions, please, put them in the chat. And Darby, if you could just keep an eye, we can interrupt at different points to take questions. Okay, so magnetic tunnel junctions. So what is a magnetic tunnel junction? It is two magnetic layers separated by a very thin insulating barrier. I think you can see my mouse, right? That's okay. And electrons it's so thin that electrons can quantum mechanically tunnel between the metallic layers. When they tunnel, they often preserve their spin direction. And because the ferromagnetic layers have spin polarized electrons at the Fermi level, the tunneling resistance, the tunneling magnetoresistance, depends on the relative orientation, the magnetic orientation of the two layers. It's different when they're magnetized in the same direction versus anti-parallel, for example. So the actual structure of things, a tunnel junction, are these cobalt iron boron layers that are the metallic layers. There's 1 or 2 nanometers of MgO, which is the tunnel barrier, and another cobalt iron boron layer that we call the free layer. So one layer is fixed by making it harder to reverse, higher anisotropy, and the other layer can be switched. And one of the remarkable things is that you can get tunneling magnetoresistances or changes that are a factor of 3. And maybe the record may be a factor of 10. But in practical devices, you can see over 100% change in resistance. So when the two layers are magnetized parallel, you're in a low resistance state, and when they're anti-parallel, you're in a high resistance state. And you can have a bistable system. In other words, at zero field, you can have 2 possible states when the materials are small. So this is an example of a 40 nanometer pillar. You're looking down the top. So you should think of these as, we call them pillars. They're more like pancakes. These are just a few nanometers thick, these layers, but 40 nanometers thick. But to some approximation, the layer magnetic moments are uniform. And so you can think of it as a 2-state object. What you can do also is switch this with current or voltage that's directly applied to the tunnel junction. So you can go from the high resistance to the low resistance state at about 400.4 volts. And here in this example, back to the anti-parallel or high resistance state with minus 0.37 volts. So you can switch with current or magnetic field. This was a very important discovery, theoretical discovery, that currents can actually act on the magnetic layers. And that's very important for this story I'm going to tell you. But for an electrical engineer, you just need to know you have two states and you can access those two states. And this device can be easily integrated, easily being in quotes, meaning that it took engineers a decade, but it could be done. That is, you can put these materials into the back end of the line and basically finish a silicon chip with these devices. So they can go in where you would normally have the interconnects between the silicon. You can put these magnetic tunnel junctions so they can be closely integrated with the CMOS logic. And the way they're integrated is you have a single transistor that acts as a switch that allows you to access a particular element in the array. And then you apply voltages and currents to switch it and determine the magnetic state. You would measure the magnetic state by measuring the resistance at low bias, and you could change the magnetic state either with magnetic field or with a higher bias voltage. A magnetic tunnel junction converts a magnetic configuration into an electrical signal that's easy to read. It means you can read the state of a very, very small magnetic element, something that just consists of maybe 10 to 10,000, 100,000 magnetic moments. So a very small magnetic volume. And they're straightforward to integrate. So they've already been integrated in the case of memory cells. You can make gigabit memories that are integrated with CMOS. So that's what people do. In fact, most major foundries, Global, Intel, we believe, also Samsung, TSMC have MRAM products or MRAM in their development line. And then what they do is they arrange it so that the bits are stable. That is, you create a situation where there's a big energy barrier between the two possible states of the free layer, magnetized up and magnetized down. And then you switch it with the idea is the energy barrier has to be large enough that these states would be stable for many, many years, but you have to be able to reverse it quickly. You reverse it quickly by applying a bias. You read it with a small bias, but you design it such the energy barrier divided by KT, where T is the device temperature, is greater than 60. And that would be a case where you could preserve information for maybe a decade. These are nanoscale, so they're non-volatile. You only need energy to read or write. So this is one of the big advantages of MRAM, is you don't need any power to maintain the state, and they can be closely integrated with logic elements. So they can replace many of the volatile memories that need a battery, for example, where you have critical information, and can be used in various types of devices where retaining the information is paramount, and you may lose power for some reason, or you want to maintain that. So large energy barrier. And I don't know if there are things piling up in the chat. I don't know if there are questions at this point.
We have two early questions. One is, why is the switching asymmetric?
Okay, maybe we'll come to that in a moment. I have to tell you why it switches first of all, and then I can tell you more about why it's asymmetric. But a hint is that there are always some magnetic fields in the problem. You've broken the symmetry by having one layer that's magnetized in some direction. Okay, so that's a hint that there wouldn't necessarily be the same energy for the magnet being up or down because there's another magnet in proximity to it. There are other factors come in as well.
Our second question is, what are the practical applications of the hysteresis?
Oh, what are the practical? You'll see. Well, one is memory. There you can have, if you have bistable hysteresis, means you can store information, and the bistability also means you can. We'll see. We can make random bits as well. Thank you for the questions. I really appreciate them. We'll keep going, and then I'll pause again for questions. So what if you want to make this into a stochastic bit? What if you want to have it such that it will be in randomly either magnetized up or magnetized down? Well, what you can do is reduce the energy barrier. There are ways to do that. One easy way is you could change the volume. If you make the energy barrier is proportional to the volume of the element. So if you make it small enough, it will fluctuate. You can also change its magnetic anisotropy, its magnetic moment. This is the permeability of free space. So you would make E be about the same as KT, maybe. So you could make this ratio smaller, and then there's the rate of fluctuations would be given by an Arrhenius law to some approximation. That is, there's a temp time which is set by the basically something related to the curvature of the potential or the anisotropy, and there's a factor that describes the energy barrier. So the attempt time is again related to magnetic parameters like the damping and the anisotropy, and you can get values on the order of gigahertz. And so that gives you kind of a limit to, or a scale for what the fluctuations could be as you reduce the energy barrier. But you can't reduce the energy barrier to 0 if you want the bit to have 2 possible states. The energy barrier is ultimately what sets the fact that you have 2 states. And this shows an example of the output of a device, time averaged, with different voltage inputs. You can sit at 0. That corresponds to the device flipping up and down, going from parallel to anti-parallel, so the resistance going from high to low. You can sit over here. This corresponds to the device more or less being in the parallel state most of the time, with some fluctuations up. And then the opposite case is here at positive voltage. You're biased toward the anti-parallel state. So you could, by bias voltage or magnetic fields, you could control the time the system spends in the different states. And one of the goals of our project, and one of the metrics of the COINFLIPS project, is how many random bits we can get per second. And we have a very ambitious goal of billions of random numbers per microsecond, or 10 to the 15 random bits per second. So we have a number of ways to reach that. We have the individual fluctuations of the device and the number of bits. So if we have a megahertz, we could have 10 to the 9th devices. So if we have a giga number of devices, we could achieve this rate, and we can balance this. It's of course better to have faster fluctuations. You could have more capacity to generate random numbers. So this is what we would like to achieve. We think this is possible with magnetic tunnel junctions, having fluctuation rates in the tens of megahertz, maybe somewhat higher rates. What could this be used for? There are a lot of ideas for what you could use these stochastic bits for. Just point out a couple of them, again, not comprehensive. One is you could do a form of approximate computing, where you represent numbers by bit streams that are uncorrelated, and you could do logical operations where you build up an answer that becomes more and more accurate the longer you wait. So this would be an example of, you need an answer quickly, you need it even if it's approximate, so you use this fact to get something rough, and then as time goes by, it becomes more accurate. It could be like an image you're taking and you want it to get more in focus, but you need it immediately to see what you're doing. So this requires bits, but that have to be uncorrelated. And because you can control the bias of these magnetic tunnel junctions, in principle, you could represent these different states to create a logic that uses these random bits. Another important application is one that was discussed in this COINFLIPS. In fact, the first talk of the COINFLIPS by Supriya Dutta, a very nice idea of doing probabilistic computing, using these as what is called p-bits, bits that can fluctuate and then interact with each other in order to solve certain kind of optimization problems. In this case, the problem was to solve a factoring problem and to design kind of a reversible circuit that used this. That appeared several years ago, and there are additional experiments that have gone on. So these are one of the applications. Here you see the energy barrier was chosen to be about 15 kT. So you had fluctuations, something like the hundreds of kilohertz or megahertz rates in those junctions. So those are some of the things, and there are many other things that people are thinking about for these stochastic magnetic tunnel junctions. Our target is on Monte Carlo simulations. So you could say it's really to enhance simulations that require large quantities of random numbers to simulate stochastic processes. And one of the key applications we're focused on is particle physics. So where you have particle production and you're trying to model the response of the, what will come out of that, as well as the properties of the detector, as well as doing the same for cosmic rays, studying the interactions between alpha particles and the atmosphere. And it turns out those require a large quantity of random numbers, 20 and a large amount of time. 25 to 50% of the time is spent on generating pseudo-random numbers, and more is needed if you need to create non-uniform or specific samples. And the same is true for these cosmic ray events. The smaller this impact parameter, the more time, up to 50% of the time, is needed, depending on the method of calculation. I'm told that for a 64-bit uniform pseudo-random number, it can take 1.3 microseconds to generate. And in a standard library, the energy cost is a microjoule for 1 bit. So MTJs can generate these bits with picojoules of energy. So that can be a huge savings in energy consumption. And so our goal is really to push this, to see is it really possible and what would be the best way to do this. And MTJs are one of the options, one of the devices that's being explored. Tunnel diodes are also being explored at Sandia in Shashank Misra's group. It's a broad exploration of what can be possible and what are the best things to work with. But we really want to demonstrate that we can have some advantage with magnetic tunnel junctions. So this is the way we're going to do it. But so what I can tell you is that we've taken a different route than the low energy barrier magnets. It turns out there can be advantages to actually working with stable magnetic states to generate random numbers. Now, this may seem very counterintuitive. Why would you use a stable bit to generate a random number? But it turns out we can do this, and we can make it very, very fast, even faster than the characteristic times associated with the fluctuations in a low energy barrier magnet. And we can do it efficiently. It's going to cost a little more energy because we have to put energy in, but not that much more. And it turns out that these kind of things we work with are also less sensitive to the environment, to the environmental temperature, device-to-device variations, and some other factors that could make them advantageous. And what we're using is spin transfer torques. So these are the torques that allow you to switch the magnetic moment, which I talked about earlier. And these are based on conservation of angular momentum. So basically, you have a fixed layer that polarizes the electrons, and a second layer that experiences that polarization. That's that free layer in the diagram. And when you flow a current, the spin polarization direction of the attendant electrons, those that are tunneling, changes. And then by conservation of angular momentum, that means there's a reaction on the magnet. That's the origin of the switching. So there's a torque because when you pass a current, you flow spin angular momentum, and that angular momentum can act on a second layer. And the basic idea of our concept is we would just put enough angular momentum to camp the magnetic moment to the equator and then let it go. And that's going to be the way we generate our random bit. That's a analogy that's not perfect, but gives you an idea. We're going to put in almost the right amount of angular momentum to be half the time end up when the magnet relaxes to end up in a spin up state or magnetization up, and half the time in a magnetization down. So the reference layer here sets the polarization, and we're going to read out the state with the tunneling magnetoresistance. And maybe this is a good point to stop again for a questions.
We do have a question. It's were the energy approximations you were given considering all the associated circuitry needed to get a probabilistic bit?
Not at this. No, at this point, I'm just considering the energy of the MTJ with a picojoule estimate. So there would be a circuit component to that as well. Usually at least double the cost. Thank you. Okay, one more question, is there?
Yep, just one popped up. Maybe out of the loop, but what is the difference between the uncontrolled and true random number?
Uncontrolled and true random number. I guess if I'm understanding the question, maybe you're asking what's the difference between a pseudo and a true random number. A pseudo, so pseudo random numbers are generated from a seed in CMOS. So they're perfectly reproducible if you start with that seed. And true random numbers would be such that you couldn't reproduce the train. There would be no way to reproduce it in some sense. They're well-defined ways, I guess, to test for randomness, but it wouldn't require any seed, and it would generate random numbers based on random physical processes.
So
Okay,
I think that addresses the next question as well, which was, are true random numbers better random numbers for the application?
Yeah, that's a great question, and that depends on the application. For example, for cryptography, it's essential to have true random numbers. For large-scale calculations, it depends. It depends on the length of the calculation and whether you can tolerate periodicities that would occur with pseudo-random numbers. But yes, it will be very application dependent.
And a follow-up is, if the environment is determining the output by an unknown deterministic process, is that still true random? I.e., there's a hidden deterministic bit that's actually influencing everything.
No, that's a very interesting question, and the environment in some sense knows the state. But of course, if the environment is really large enough, we don't care. That's a good question. I mean, if you had some way of probing the environment, you might be able to back out the stochasticity. But we're going to take the usual thermodynamic approximation that the environment is just huge and has many, many degrees of freedom, and there's really no way we could learn it, essentially, which should be a good approximation, or a very, very good approximation. Okay, great questions. Thank you. So these are actually concepts for spin transfer torque that were introduced in 1989, and they really changed the whole field of magnetism, allowing you to manipulate magnetic materials with voltages and currents. And so this is what some of the characteristics then when you have spin transfer torques. I showed these pictures before. You can change the magnetic state of the free layer with a magnetic field. You can change the state with a voltage. And I'm interested, what I show here is when you apply a voltage or a current pulse, you can say, what's the probability of switching? And the blue line represents the probability of switching half the time. So as you go to nanosecond pulses, you can see you require more and more current or more voltage to switch the device. And this is the so-called ballistic regime. This is the limit in which the current is most of the angular momentum in the current is going into, or fraction of it, large fraction is going into the magnetic layer to reverse it. If you plot the current versus 1 over the pulse time, you get a straight line. And that's also, that's telling you that the current times the time minus some constant is what's conserved. That is, you have to put a certain number of charges through the device in order to get it to switch. And this is the line we want to operate on. We want to get to the point where the junction is half the time going to stay in the original state, and half the time it's going to switch. And it turns out these devices don't actually switch like spins rotating. If you do a modeling, and even if you do measurements, there's more complex dynamics. So this would be an example of a micromagnetic simulation. You start out magnetized up, you end up magnetized down, but during that process, you nucleate domains, you have domain wall propagation, and so on. The key part for us is that the magnets always relax in a fraction of a nanosecond or so. So you mostly don't get stuck in a state where there's another state. You really have two well-defined magnetic states at the end of the day. So we're going to use the fact that we can create angular momentum that leads to half the time up and half the time down. And we're going to build, we work with these magnetic tunnel junctions. These are materials, again, which are built in layers where you have several magnetic layers separated by a thin insulator. You can always make it out here. That's the MgO. There's sometimes 2 MgO layers, one on both sides of the free layer. This is a 60 nanometer pillar. This is the contact on the bottom. This is the contact on the top. There's a 46 nanometer nanopillar. And this is a 21.5 nanometer pillar before you've actually polished the oxide down and made the top contact. So this is an oxide layer. And so all the voltages are applied here. And this is the part that gets integrated into the CMOS. As you expect, as you make the junction diameter smaller, the resistance goes up. The resistance is inversely proportional to the area of the junction. So you have flexibility in the size you choose and many other parameters you can take when you make these junctions. And it's very sophisticated technology, actually, particularly carving out these nanometer scale elements. And because the magnetic materials usually don't etch by reactive etching, you have to do a physical process. And so you have to worry about where the material goes. And you don't want it to be deposited on the edge of the MGO, which would shunt the device and actually not make it a tunnel junction. But industry now is routinely making junctions down to 20 nanometers. They're in technology, and labs have gone down to 7 nanometer, maybe even a little bit. So single digits are possible for these. So these can be integrated into the most advanced semiconductor nodes, both in the size and also in their operating conditions, the voltages and currents that are needed to operate them. So this is now a measurement of a junction that's 40 nanometers, and we're applying a pulse through this bias T, and then we measure the junction state simply with a voltmeter. So the red zone is where nothing happened. The junction stayed in its original state, in this case, the anti-parallel high resistance state. The black zone is where it switched with nearly unit probability. And the blue line, the blue dots represent the measured 50% point of switching. You can see we've done some interpolation to emphasize or take more data in the range where something interesting is happening. And this light blue line is the theory, is the conservation of angular momentum line. That's the line that describes this ballistic limit. And you can see we can get the same kind of behavior for P to AP as AP to P with slightly different voltage scales. And that asymmetry comes from both the magnetic fields that I told you about earlier, as well as the fact that the torques, the spin polarization can be different from the two different geometries. You can have different amount of voltage to spin current conversion depending on the direction of the bias voltage and the state of the junctions. Now, so the conservation of angular momentum says basically you have to put this many charges through the device, some characteristic time times the critical current, and this is the number of charges that flow, the pulse amplitude times the time, and part of that angular momentum goes into dissipation. So the higher the current, the less the fraction that goes there, and that's why. Well, this is what gives you this blue line, in fact. But you can think that roughly to get to 50%, you have to put the number of charges you have to put through. I times T has to be about the number of magnetic moments divided by 2 of in the magnetic layer. So if you have 10 to the 5th moments, you need 5 times 10 to the 4 electrons to traverse that layer. That's roughly a way to think of it. If you're working as a memory, if you want it as a memory, it turns out stochastic processes are always important. If you want it to be reliable, you have to apply a voltage or current much larger than the threshold, so you get down to very, very low errors for the right error rate. So this is where you'd operate your memory, and you'd have to decide how much error correction you want, or how much, to decide how you're going to build that memory. What we're going to do is operate up here at 50%. That's where we're going to operate a device to generate random bits. So that's the game here, is to use the angular momentum to generate the random bits, but operating devices that would be similar to those that are used in memory. The main thing is we lower the energy barrier a little bit, so we don't have to apply as much energy. We don't need the stability really over long periods of time for these kinds of devices. Okay, so I'm going to now get into more details about our approach and some of our results. Are there any questions at this point?
Aren't any at the moment.
Oh, good. Okay, so I'm going to tell you about our approach here. So the approach is now to work in this ballistic limit. Ballistic means we apply nanosecond pulses, and ballistic means that ideally the magnet evolves from some initial condition and is not subject to thermal fluctuations, magnetic fluctuations during the time the pulse is applied. That means actually pretty high amplitude pulses, but this is a reasonable approximation when you have nanosecond pulses. The randomness here comes from the fact that the magnet starts in a thermal state. So in a Boltzmann state, that is, it's distributed, it's most likely to be at the lowest energy, aligned with its anisotropy direction, but there's a probability that it will be aligned at some angle just because there's thermal noise. And what the pulse does is it amplifies that thermal noise. So you kind of illustrated here what the Boltzmann distribution might look like. When you apply a pulse, there's kind of a dividing line. Those states that are above the dividing line or below the dividing line will switch, and those that are below the dividing line expand, but they don't cross the equator. And this is, again, a simple model, a so-called macrospin model. And what's interesting here, even in the macrospin model, is that they're really, at the end of the pulse, right at the end of the pulse, you really don't have a lot of magnetization that's at the equator, like I described in a simple analog, but you either switched or didn't. And this is essentially because the spin torque is exponentially amplifying the fluctuations. So you're more or less getting a bimodal distribution during or right after the pulse. So this is the picture, and this junction state is mainly random because of the thermal distribution of magnetic states, and we've also done more extensive modeling. And so we activate the junction. You could say it is like a coin flip, but we're starting the coin in a well-defined state. So it's like starting with heads and flipping and then reading. And we can reduce the energy barrier again because we don't need to have stable states. And we've distinguished this by the fact that it's activated. So we're not letting it just fluctuate, but it also means that we can set the time scale of the device by the way we operate it, namely the pulse time. And it turns out nanoseconds is roughly where you minimize the energy, where the time scale of the pulse is near that characteristic time of the dynamics is where you minimize the energy required to generate these bits. So this is now a plot of the probability versus pulse amplitude for 1 nanosecond pulses, and each of these points represents 10,000 events. The event consists of reading the state, applying a pulse, then reading the state and say, did it switch, did it not switch, then resetting the state. And this is done with a digital to analog converter at a fairly slow one, 100 kilohertz. But you can see we get a very nice sigmoidal form. And what we're going to do is work near the 50% point. And the nice thing about this limit is also there are analytic expressions that allow us to get out some of the material parameters and fit the data. This is really only true in the very high pulse limit, but they work at least qualitatively. They capture the data, actually even quite quantitatively. And we get out some of the important characters, time, the threshold voltage, and we can get information about the energy barrier from long time measurements. So we know the stability factor from different types of measurements. So this is our operating point. And then we can just take samples. So this is an example of, I think, about 10 million samples, where we segment the samples into hundreds, groups of 100. And we say in that group of 100, how many cases did the state of the junction change? We call that a success. So you'd expect if it's a perfect coin in a sample of 100, it would switch 50 times. And then we just repeat that, and you can see that we get a stream of bits. It sometimes has very large numbers of flips or very small numbers, and we get an average. Average is not exactly 0.5, it's 0.5027. But then we can take a histogram of the data. How many times did it flip? 70 times, how many 50? And we expect this is a Bernoulli process. We expect this to be a binomial distribution, and we're fitting it to a normal distribution, which is an approximation. And it fits perfectly, you could say, or very well, with the only parameter we need for the fit is this measured probability. The variance and everything else are just related to that. So this tells us we're on the right track. we have something that looks like a coin. And I mean, I think another interesting thing is we didn't see any drift. This measurement took probably 10 hours to do. We were doing about 1,000 bits per second. You'll see that that's something we want to go do much faster on. But this was our first experiment with the electronics that we had when we started this project. So this is nice, and we can be much more quantitative. What we've done is also implement several statistical tests for the randomness. One is the so-called NIST tests, which are tests that essentially look for the suitability of a random bit for cryptography. And I'm sure there are experts listening that know much more about these than I do. I will not say I'm expert in this, but we implemented this, and you can see with one exclusive OR, taking alternate bits and exclusive ORing them, we pass all of the NIST tests. And we believe the exclusive OR is needed because we have a slight bias in the bits. Our probability is not exactly 0.5. So that's good news. And we've also, with Shashank Misra, we've looked at now generating 8-bit uniform random numbers. So uniform distribution of random numbers from 0 to 255. So we simply take a stream of 8 bits and segment them into, and call that our number. And then we plot the distribution again for the similar number of random bits that I showed you before. And this we test with different statistical tests using the so-called KSS test. For those that know, we've shown that this also satisfies those tests for randomness. So it looks like we have a very good way to generate random numbers. There are no obvious correlations that are coming through, which you could imagine. First of all, would the spin torque really generate a uniform random number? I mean, it's a different type of interaction than, say, a magnetic field or an anisotropy. And secondly, of course, in any real experiment, there are all kinds of ways that noise could come in and induce correlations. That doesn't seem to be the case here. Okay, so maybe that's a good, I see there may be a few more questions.
Indeed. Could you clarify how the XOR removes the bias offset?
Yes, well, the XOR, you can show mathematically that if you have a probability of 0.5 plus epsilon for 2 bits, after you do an exclusive OR, the probability is 0.5 plus 2 epsilon squared. So you get a higher order, you get closer. If epsilon is small, you reduce the, you get closer to 0.5.
And our other question was, are there easy manipulations of a random but somewhat biased coin that can turn its output into a similarly random but fair one?
Yes, I'll just say yes. That's in fact one of the major emphasis of our coin flips, is to show how you can do these kind of things. And I'm sure that one of our world's experts is listening here, but one of our team experts, I wish are listening. So yes, the answer is yes, and maybe we can come back to that at the end if we're in discussion. Thank you for the questions. Ready to move on? Okay. So the other thing we've been interested in practical and also in theory is how sensitive is this device to temperature and other environmental factors. I mean, as I said, basically this turns thermal noise, KT, into a random bit. So you'd expect that the environment should have an important role. For example, for the super paramagnetic devices, the devices that fluctuate simply by reducing the barrier, the switching rate is exponentially sensitive to temperature. So you want to know, if you're going to build a device, how sensitive is it? How accurately do you need to maintain the temperature, or do you need to do something to adjust it? How much overhead do you need? And so the less sensitive is, the better, but you would expect sensitivity. So what we've done is we've changed the temperature of the environment of our device by 10 degrees, 5 degrees above and 5 degrees below, and measured the probability of switching, keeping the bias constant as if we're operating this with an optimized voltage bias. And you can see then for 5 degrees above, the probability goes to 0.53, and for 5 degrees below, it's 0.47. And so we can compute then the derivative of the change of P versus T, and see how that sensitivity works. Higher temperature leads to more switching. That's kind of makes sense. So let's see. So we did this now as a function of pulse duration. And you can see then the points I showed you down here were with 1 nanosecond. We can do this for both types of transitions, AP to P and P to AP. And we can model it in 2 different ways. One is this macrospin model, which really only applies for very, very short pulses. And what's interesting here is that if you work out the model, you find dp dt does not depend on material parameters. This is kind of a surprise. It just depends on log 2 and 1 over and the temperature inversely. So this is quite a remarkable thing, actually, that you'd think that all kinds of material parameters come in, but in this ballistic limit, they don't appear to. And so if you put in the 300 Kelvin, you would get 1.16 times 10 minus 3. So that's kind of that's the fundamental limit. We're at 0.05. We're like a factor of 4 higher than that in our measurement. We checked then 2 different ways. We checked another way. With collaborators, with Golem and Mossad and Avik Ghosh, they implemented a macrospin Fokker-Planck analysis, and indeed they see that at the lowest times you approach this limit and then it saturates. And they also make a prediction for how this should vary with pulse duration. We're above the prediction, but the trend is the same. And what this tells us is if we want to maintain a variation probability of less than 0.2%, we need to maintain the temperature variations to less than 0.3 Kelvin. So small variations. This is possible in the lab. Whether this is possible in a chip, one has to see. But we now know what the conditions are to maintain this a certain probability. So this is now we can compare our approach and what we've investigated to other approaches. There's superparamagnetic tunnel junctions. There are a whole variety of these. We've looked for cases where this was measured. So this we saw for a 1% change here, there's a 16% change in probability. Spin dice are devices operated with 200 nanosecond pulses. There the variations are close to 11%. And for the devices we've studied, it's about 1.8%. So there's a big advantage to working in this ballistic limit at short pulses. So that we think is going to lead this to be an important way to work. We've also looked at sensitivity to other things, like how accurately can you control the pulse amplitude. And this also turns out to be favorable for small pulses, because short pulses, short duration, because the switching probability is dp dt is smaller for short pulses. It gets steeper as you apply longer duration pulses. And we've also looked at what about the sensitivity to pulse variations, delta t over t? And here the trend is opposite. In some sense, as you go to shorter pulses, you have to reduce the variation in pulse duration to maintain the probability. So these are things that that are important from the circuit point of view, and for operation is what are the variables you really have to control accurately to ensure your probability variation is within some range. And finally, we're working also more on the modeling side. We measure tens of devices, but we can't it's hard for us to do, say, a systematic variation of device diameter or material properties. That requires lots and lots of measurements, lots of devices. But working with Golem, Morshed, and Avik Ghosh, they've studied in this Fokker-Planck model what happens for device diameter variations or material parameters like the magnetization varying. And again, the ballistic limit is favorable from that point of view, which suggests that this is the way to go. If in arrays, you can reduce the variations that associated with material fluctuations, which is of course very important in magnetic devices, including in MRAM. But MRAM, the conditions are really, you need the barrier to be larger than something. So it's a little bit different than what we're asking for here. So that's all good. So the question is, and my colleagues now are asking me, how are we going to show that this is useful for Monte Carlo and other calculations? They want a lot of bits. They want more than 10 million bits. They want 1 million times 10 million bits. So they've been pushing us, and so we've done a number of things, and we're working really hard in this direction. I should say that, you know, getting 10 to the 12th events is even something that's not very common to do when you're testing MRAM. So this is kind of a thing, we think this is a kind of frontier. So we decided to engage actually a particle physicist. This is a colleague in my department, Andy Haas, who knows a lot about measurements. He's in charge of the FPGAs for the LHC. And we told him about this problem, and he said, well, this is really easy. I said, okay. So we got an undergraduate involved, Andrei Dubrovsky, who's the son of a particle physicist. And together they teamed up and they built this FPGA circuit, which can both apply the pulses and measure the state of the junction. So everything that we had, our pulse generator, our digitizer, are all now on a 2K chip that they made, which is connected to the device. And they've been already able to generate 10 to the 7 bits in 3 seconds. So that's a 1,000-fold increase in the data rate I showed you earlier. That's, I think, good news. And that's one approach so basically, and the FPGA circuit is very nice because it gives us also ways to manipulate the data. In fact, in some way, well, not manipulate, but you could say do calculations. If you wanted to do exclusive ORs or so on in the hardware, you could do it. So it could be a way also to make the bits fair, or do operations on them even before you process, even, you know, for a calculation. That's one way. And the other way we're doing it is we've improved our electronics. Basically, we've purchased a faster digitizer, a digitizer that can digitize at 8 gigasamples per second, thanks to Sandia, and also has 12 bits of resolution. And so we use our AWG, and it communicates with this essentially a scope. This is an example of a 10 megahertz acquisition. We reset, we read. This is to verify. We write the 1 nanosecond pulse, and we read. And then we use this. This is a case where the write was set to be such that you're near unit probability. We're testing things out now. And this can be done at 10 megahertz. We believe we can go faster. In fact, there may be things we don't need. If we test the reset and we don't need the read, we certainly can do this much faster. We expect to be able to get to 20 megahertz rates, which would mean 10 to the 9 bits in a minute, or 10 to the 12 bits in a day. So we're hopeful we're going to get there. There's a lot of moving parts here to getting this data into the format we need, and being sure that the bit we're really requiring it without making, say, read errors. In other words, we want to be sure that the read is accurate, reflects the state of the device after we've written the write pulse. Okay, I want to make maybe one last comment. I'm coming to the end. I want to say that there's many other ways one can work. I've talked about magnetic tunnel junctions, where you polarize the electrons through the fact that they tunnel from a ferromagnetic metal into another ferromagnetic metal. And so you're using the fact that the electron density of states at the Fermi levels are polarized. There now is another way to work, and that is using what are called spin orbit torques. That is, you can create spin currents and spin accumulations by passing a current laterally, and that can generate, through what are Rashba interactions, or what are called the spin Hall effect, an accumulation of spin on the surface that can act on a magnetic layer. And what that enables is devices that are 3-terminal, where you separate the read and the write. I believe this is a way you can, the spin currents, here's the free layer, here's a reference layer, can flow this way, and the read now is separate. So you could almost forget about read disturbs, because you can optimize the read circuit separate than you can do for the right circuit. And this is also part of our COINFLIPS effort. Jean Ann at UT Austin is working on this aspect. And this is very nice because it principle allows you to optimize devices in a different way. But the same concepts that I've told you about, these pulses to activate the junction, could be a way to operate these devices. And so this is one way to go in the future, where you have a 3-terminal device and different ways of injecting the spin and creating random bits. Okay, so let me summarize. I've shown you that we can use these magnetic tunnel junctions to generate random numbers at tens of megahertz rates, that the resulting bit streams can pass multiple statistical tests for true randomness with only one XOR. And we've seen that these nanomagnetic devices are less sensitive to temperature changes than those that operate in the thermally assisted regime, say for long pulses. They can be less sensitive to pulse amplitude, to device, to device-to-device variations. At least that's what our modeling says, and more sensitive to controlling the pulse. And I've showed you we're working toward much larger data sets with 2 approaches. One is this FPGA approach, where we build our own circuits, and the other is using this high-speed analog to digital converter. And so this work was largely was published. Most of it was published in PR Applied. We've also been collaborating with Shalu Rikija's group at UIUC on modeling, and we have I think, a very nice modeling paper on this, which also compares our approach to some of the CMOS-based approaches to generating random bits. And this is also a summary table that shows some of the, I'm sorry about that, that shows some of the comparison within the magnetic devices that report the things we've done, the bit rates. So in the thermally assisted regime and super paramagnetic regime, it's hard to get the fast bit rates that we're talking about because you have to adjust the energy barrier, and this attempt time is gigahertz. So maybe this is a good place to stop and take questions. And thank you for your attention. I hope you found the talk interesting and informative.
Thank you so much, Andy. This was excellent. We do have a couple of lingering questions in the chat. The first is, if P to AP and AP to P have slightly different behavior, does that mean the probability of a bit has dependence on the previous bits? And if so, can that be seen in the statistics for the bit stream?
Yes, what we haven't. Yes, the answer is you would see it, but it would depend on how you work with the how you generate the bits. In the case of our experiments, we always start from a known state, so we don't generate these correlations. So we always apply this. Let me show you here. This reset pulse sets the device in a known state. So we're always talking about the same transition. We're not switching from P to AP and then AP to P. But if we were, we would see those kind of correlations that you mentioned.
And our second question is, could you summarize the conclusions when comparing to CMOS-based TRNG?
Yeah, CMOS-based TRNG. Well, I could, but that's a large landscape. So I'd say that there's the landscape of CMOS-based PRNGs, I guess, or other types. Was it P there?
T as in true. Yeah.
G. Oh yeah, then I'd say you have to go look at these papers by Shalu and others. There's a huge landscape of different approaches, like chaotic. There's ring oscillators. There are many approaches. What we've seen, though, in general, what I would say the overall summary is that these devices that I'm talking about are much more compact and require fewer elements. But I don't want to go too far, because you really have to start to think then about specifics of the CMOS to make a real valid comparison.
Could you throw those references back on screen? So
yes,
we can.
In fact, I would encourage you to look at this paper. That's my MRAM summary. This paper here is a good one, a good starting point. And there are additional papers I could send along to you, Darby, or that you could distribute that have these kind of tabular data. with comparing different factors.
Excellent. Yes, and feel free, and I'd be happy to send those to anyone that wants to ping me, and I can send those out.
Okay.
We do have a question about SOT versus STT. Specifically, how do you anticipate the 3-terminal SOT device will limit the density of the devices, or is that not really an issue?
Oh, that is an issue. The issue is that you likely need 2 transistors to operate the SOT, and you're likely to need more. So you're likely to need more area. You will need more area. There are concepts that combine SOT and STT. They're so-called 2-terminal STT, but that requires some fine tuning, at least in my opinion. What's nice about the SOT is that you really have separate controls. So you will lose density. There are several people who believe you gain speed. That is, there's experiments that indicate you can switch faster. So you may end up being able to, and you may, I think so the positives on a very high level are that the readout signal can be larger. You can optimize the tunnel junction to have much larger magnetoresistance, whereas, for the STT, the tunnel junction has to be a relatively low resistance area product junction, so you can't get the maximum possible MR. Usually the magnetoresistance increases with the thickness of the barrier because you get better spin filtering properties. So you gain that way, and you may gain in the speed. So if you want to operate at, say, hundreds of picoseconds rather than nanoseconds, that may be, so that would be the positives. And I'd say the negatives would be the increased area and maybe the increased complexity of the CMOS, more CMOS needed per bit.
I invite anyone in our audience to ask one final question. I do have one, but I think you answered it when you answered your AP to P question, and it was you had shown an equation with the gamma, and it had a rate form that to me indicated Poisson statistics, and in which case you would definitely see a long bit stream dependence and a bit of memory.
Yes.
But with the reset, I imagine that's not an issue.
I think that was near the beginning, right? When I was talking about the relaxation rate, and I was just considering the so-called low barrier magnets. Yes, absolutely, agreed. That would be a Poisson process.
Excellent. Well, everyone, let's thank our speaker again. Andy, this was a fantastic talk and really thorough, and I really very much enjoyed it. I hope our audience did as well.